Hi, everybody. Okay, today's lecture is going to be on section 2.2, which we're actually going to do first out of chapter 2. And it's on separable equations because those are the simplest kind of first order equations. So I prefer to start with that. This is actually the second time I'm doing this lecture. The first time I forgot to have the mic on. So let's redo it and do it with sound. Okay, so I'm going to share my screen so you can see some, whoops, over here. I need to share my screen so we can look at, um, well, actually, I don't want to share it yet. Let me go back, close that. I want to use my dock camera to start with. Okay, so a general first order ODE. And in chapter 2, we really begin to learn to solve ODEs. In the first chapter, we were sort of showing lots of characteristics and things we're going to study later in much more depth. But now in chapter 2, we really begin to solve the ODEs. So we look at a general first order ODE. Excuse me. That's anything that can be written in the form the derivative of y with respect to x. So we think of x as our independent variable, y as a dependent variable, is some function of x and y. So we're going to learn how to solve lots of special cases of that. In the absolute most general one, you don't know how to solve it. But an equation is separable if it can be written in the form where, again, remember in this Leibniz notation for derivative, you can think of multiplying by dx. You can treat those pieces like you do a fraction. So let me multiply both sides by dx. And if I'm lucky enough so that the equation can be written so that it's only functions of y on one side and only functions of x on the other, that's a separable equation. And the method of solving it is really quite simple if it separates. If you hear some snoring in the background, that's one of my old golden retrievers who apparently thinks separation of variables is kind of boring. Okay, so he's snoring through it. So the only thing you have to do if you have a separable equation is just integrate on both sides. What you do to one side of the equation, you do to the other. And now if you can work out those integrals, you're done. In principle, you're done. And solve for y if you can. If you can solve it so that you say y equals blah, blah, blah of x, that's an explicit solution. If you can't solve it explicitly for y, sometimes all the best you can do is get an implicit solution. Okay, so now let's go back and look at some examples with some graphics. So now I'm going to share the screen. Okay. Whoops, I want to go back so you can see me. Let's set this up a little differently. Get to the live camera and then share the screen. And now where did it go? There it did. Okay. Okay, so now when you look at this equation, you want to solve this first order equation that they give you here. So it's dy dx is x squared over 1 minus y squared. Okay, and to solve that, I'm going to multiply on both sides by dx and by 1 minus y squared. So when I do that, on the left, I'm multiplying by dx times 1 minus y squared. So the dx will cancel. On the left, I'll have 1 minus y squared times dy. And when I multiply by dx times 1 minus y squared on the right, I get the 1 minus y squared cancels, so I get an x squared dx. So notice the left-hand side is functions of y only. The right-hand side is functions of x only. And now when you look at that means it's separable, it's separated, and we can integrate on both sides. You cannot do this, you can't do the integration if any part of x is mixed up with the y stuff or vice versa. So it's not in this case, so we can just integrate. When you integrate 1, you get y. When you integrate y squared, you get y cubed over 3. When you integrate x squared, you get x cubed over 3. And you get an arbitrary constant. So we don't need one on each side because they're both arbitrary. So you lump them together and put it one on one side. So we'll put it on the side with the x. Okay. And then they multiply by a 3 just to make it look a little prettier. So we have 3y minus y cubed is x cubed plus c. So in this case, we have an implicitly defined solution. Y is a function of x. You can't solve explicitly for y. And then they graph a bunch of those curves for different values of c. Okay, so when you just have a differential equation and nothing else, then all you get is the solution in terms of a constant that has to be determined by other information, or it's just an arbitrary constant. Okay, here's another example. And now I'm going to switch to, I believe, and work this out a little better. I want to look at the example. Dy dx is 3x squared plus 4x plus 2 over 2 times y plus 1. Okay, so they skip a lot of steps. Let's go back to my .chem. Oop, sorry, that wasn't what I wanted to do. Here we go. Okay. All right, so here's our problem. Okay, so we're going to multiply by both sides by 2 times y minus 1 times dx. Okay, so when we do that, on the left-hand side, we will have, ignore the integral signs for right now. So we will have 2y minus 1 times dy, and on the right-hand side, we'll have 3x squared plus 4x plus 2 times dx. So only the x stuff on the one side and only y stuff on the other side. And there's an equality sign in between. So I can integrate. So I do. And now I just do the integration and be a little careful. Okay. All right. So when I integrate 2y, I get 2y squared over 2, which is y squared. When I integrate minus 2, I get minus 2y. When I integrate 3x squared, I get x cubed. When I integrate 4x, I get 2x squared. And when I integrate 2 with respect to x, I get 2x. And I need an arbitrary constant somewhere, so let's put it on that side. Okay. Okay. Now that's an implicitly defined solution, y in terms of x. Okay. In this case, we actually can get an explicit solution, but it takes a little algebra work. And how do you do that? Let's complete the square in y. So take half the coefficient of y, that's minus 1. You square it, you get plus 1. Add that to the left and add that to the right. Okay. Now this on the left-hand side now is a perfect square. So that's y minus 1 quantity squared. And on the right, I have whatever I have, but notice that c is an arbitrary constant. So c plus 1 is another arbitrary constant. So let's just call that c tilde. As we get used to doing this more and more, replacing arbitrary constants, we won't even rename them. We'll just call it c, 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 because unless it's specified, it doesn't really matter what you call it. Okay. So now we have this written as y minus 1 squared is equal to this. So now we can start to solve for y. Take square roots on both sides. So you get a y minus 1 on the left. You get a plus or minus square root in this thing on the right. And you add 1. And now you have an explicit solution for y. Okay, so that was a little bit tricky algebra to get that, but it's not too bad. Now we still have that arbitrary constant. How do you ever get rid of an arbitrary constant? You need to be given some kind of condition, often an initial condition at x equals 0. So suppose they give us the condition that y at 0 is plus 3. Let's think about this carefully for a minute. If y of 0 is plus 3, I have a plus or minus. I need to know which one I'm going to be using. Well, this is a 1. The square root itself is something positive. So if I'm going to get y to have the value of 3 near x equals 0, I better be adding something positive. So in order to do that, that means in order for this initial condition to ever work out, I better take the plus sign with the solution. Okay, and so keeping that in mind, and now using the initial condition, in other words, saying y is 3 when x is 0. So I'll get 1 plus, for the reason I just explained. Now x is 0, x is 0, x is 0, c tilde, which I just called c again. And so that gives me 3 is 1 plus the square root of c tilde. So that says the square root of c tilde, that should be tilde. It doesn't matter. They're arbitrary constants, but just to avoid confusion for the moment. Okay. So that says the square root of c tilde is 2, so c tilde is 4. Okay. So the solution of our original equation with this initial condition is exactly what I've written on that last line. Okay. Um, suppose I gave, well, okay, let's go back to the let's go back to the screen share. Okay, so we had computed our solution, so we did all this. Um, here, now let's look at it if they give a different initial condition. Suppose they give the initial condition that y at 0 is -1. Okay, so you can use the explicit solution we had or the implicitly defined solution. It kind of doesn't, it really doesn't matter. It just affects the way you compute C, but in the end, your solution is correct. So now I can plug into this implicitly defined solution when x is 0 and y is -1. So I get -1 squared minus 2 times -1 is equal to 0, 0, 0, c. So solving that, that says c equals 3. So the implicit equation looks like this. And if you wanted to try to write down the explicit equation, well, here was our explicit solution. They're using c where we use c tilde. You could do the same calculation with the initial condition. If you use this explicit solution, now y at 0 has to be -1. To have a chance for this solution to ever be -1, you're going to need to use the negative sign. Otherwise, when you take 1 plus a square root, you get in something positive. You could never get a negative number. So we're going to need 1 minus the square root. So you could use this to just as well um, solve for the initial condition, in which case you put in -1 for y and 0 in for x. And again, you have to use the minus, that's obvious. And so you get c equals 4. And so here's the solution in this case. When y at 0 is -1, here's your explicit solution, which is almost the same thing we had before. It's a different sign right at the in front of that square root sign. And on this graph here, what they've done is they graphed a bunch of the equations for different values of c. Notice something that as when y equals 1, well, okay, so well, let me not worry about that yet. Okay, let's not worry about that yet. Okay, so we'll come back to that. Okay, so this is the initial condition we worked out before. Y of 0 is 3. You have to use the plus sign. Here's what we got. And here's the solution on the graph. The green piece is the solution for this exact equation. Okay. Okay. All righty. So again, here's the differential equation we just solved, the first order ODE. Here was the second initial condition we used. You can write it either as an implicit solution or an explicit solution. And notice that when you write it out this way, you could play around with the algebra a little bit and express it in the form 1 minus the square root of x plus 2 times x squared plus 2. Okay. So the domain of this function, what's under the square root sign, has to be positive The second term, the x squared plus 2 is always fine, but the x plus 2 has to stay positive. So that means x has to be bigger than minus 2. Okay. And when x is minus 2, actually, that gives you, when x is minus 2, that makes the square root 0. That says y equals 1, which makes the denominator right here in the original ODE be 0, which says that dy dx is vertical. That is, the tangent line is vertical there. And you can actually see that when you look over here, okay? And conversely, the domain you can tell by looking for the vertical tangents, but that's a unusual way to do it. It's not very useful, really. Okay, let's look at another initial value problem and try to see if we can solve this one. So dy dx is 4x minus x cubed over 4 plus y cubed. And they give us the initial condition that y at 0 is equal to 1. Okay, so separating the variables, that is multiplying through by multiplying through by 4 plus y cubed times dx, you get 4 plus y cubed times dy on the left, and 4x minus x cubed dx on the right. So on the right, only things involving x. On the left, only things involving y. So we can integrate on both sides since we have things separated. And now when you integrate 4, you get 4y. Integrate y cubed, you get y to the 4th over 4. Integrating 4x gives us 2x squared. Integrating x cubed gives you x to the 4th over 4. There's a minus sign out in front, and a plus c. Okay. And if you wanted to write it a little prettier so that the powers go in decreasing order, and if you like the coefficient of the highest order term to be 1, just multiply this equation by 4 and rearrange things. So that's what they do to get to this step. And because little c is an arbitrary constant, we could just as well continue to call it little c, but they change it to capital C. That's okay too. Now the initial condition they gave us is y at 0 is equal to 1. So you plug in x equals 0 and y equals 1 in the equation above. And when you do that, well, this is a typo down here. Yeah, that's a typo. So let's switch to the dock camera for a minute. Well, let me get this solution written down first. Okay. Yeah. Okay, so now let's go to the dock cam. Didn't mean to do that. Okay, so here's the solution we got to that ODE. And the initial condition they gave us is y of 0 is 1. Okay, so now you plug in y equals 1 and x equals 0 into this formula. So you get 1 plus 16 times 1, 0 and 0 equals c. So that says c equals 17. So the solution of the original initial ODE with the condition y of 0 equals 1 is exactly this equation. Okay. All right, so now let's go back to our lecture notes. Okay, so there's the solution that you get down here. Okay, I see. So I misread this, but they didn't do the calculation for you, they just assumed you did it. Okay. So here's the general solution to the ODE, but with the specific initial condition, and this is a typo, it should be 301, because it's when y equals 0, when x equals 0, y equals 1 is exactly this. Okay, and so the particular graph of the solution, the graphs of the solutions are down here. You would not be plotting that by hand. That you have to use some kind of software to do that, otherwise it gets incredibly messy. Okay, so the points that they put in here in blue are where you have vertical tangent lines. Now, where would you have a vertical tangent line? You would have a vertical tangent line when the derivative becomes infinite. Well, the derivative is given in terms of a polynomial function. So where does the derivative become infinite? Where the denominator of the polynomial function becomes 0. That is where y cubed plus 4 equals 0. Or in other words, where y is the cube root of minus 4, which is about minus 1.59. And if you plug into this solution and look at the corresponding x values that you get, and that's about 3.35 plus or minus. You get 2 because you have to, it's an even polynomial in x. Okay, so those are those 2 points that they plot. That's where the tangent lines of the solution become horizontal. Okay, we're not going to go on to that. So basically, separable equations are really easy. If you have one, you just separate the variables, making sure you do not leave any piece of x or y mixed up with each other. They have to be completely separate on opposite sides of the equation. And then the trick becomes, do you remember calculus 1 and calculus 2 well enough, excuse me, to actually do the integrals? The ones we did here today, I gave very easy examples where it's just polynomial functions, but that's not how it's going to go in most of the homework problems or on the test. We have to work harder than that. And so when we have a Zoom live class, when we go over homework problems, you'll see you have things that involve arctangents, secants, all kinds of, you might even get things that involve partial fractions. All the tricks you learned in calculus 2 now come up in solving these integrals, because once you know what kind of equation you have and you set up how to solve it, then it becomes a calculus 1 and calculus 2 problem, which can still be hard and tricky. That's why you really need to know those 2 subjects extremely well to do well in this class. Okay, so hope you enjoyed this. Now go try your homework on section 2.2. Remember, the quiz on everything in chapter 1 and section 2.2 will not be until week 2. Okay, so we'll be a week behind on the quizzes, at least for a while. Okay, that's it. See you next lecture. Bye.